Hello, welcome to another problem session. So today we have a problem in magnetism, actually real magnets. So let me explain the problem to you. There is a magnetic field that kind of goes around this z-axis. Some of you may know that this is maybe a current carrying wire and then it's going around. So it's kind of that kind of magnetic field. And I'm going to place a magnetic dipole of this magnitude at some point here in this. So this is given in XY plane. This is origin O, and everything is given reciprocal to origin O. So in the magnetic dipole has a direction in that direction, which is 15 degrees to the x-axis direction. A magnetic field is given by this formula, which you can write. This whole thing here can be written as just a phi hat in a going phi hat direction in a like a cylindrical theta hat direction in cylindrical coordinates. Cylindrical unit vector. It's just saying it's going in circle, so that's the direction. Or you could write that as if this is the angle theta, we're looking at the point from the origin, this thing theta. So this would have been written as cosine theta I hat minus sine theta j hat, and that's probably easier to manage than x and y like that, because x will be the distance I am r cosine theta, if this is r, and then y is just r sine theta. And I think I noticed this should be square root here. Okay, so that's the error notice. Okay, so it's a b, and so we're supposed to find torque. You're supposed to find torque on this magnetic dipole at this instant. Find force on that magnetic dipole, and then find energy of the magnetic dipole. Okay, so magnetic dipoles. What are the magnetic dipoles? You probably know that regular magnets, you have a south pole and a north pole, and you can't separate them, and there may be a distance d apart from each other, but we can't separate them. If you can break it down smaller, go to a point, you still have a south and north pole, even a point. So there is a property that you can assign, kind of analogy with you have a minus and plus charge with the distance d is minus q plus q and distance d. Then you keep separating, and then you keep the same charges. You keep increasing the charges, not same charges, and keep reducing the distance. So minus q prime, q double prime, distance d prime. Eventually a point, you can place minus and plus right on top of each other, but we're not doing that. Is as the limit to a point, just limit. If we add a point, then it will of course go plus minus q will be 0, and we look at the q times d, this product, and this is product is called electric dipole moment, right? And over here, even as a point, we can assign a p to it, and we can keep the direction same as going from, as if it had a south pole on one side and a north pole on the other side. It's like that. Even there is no way to tell q and d here, because they're going to this limit is q goes to infinity and d goes to 0, but p goes to finite. This is kind of weird limit. It's just basically you're thinking how to think of a property all by itself, not associated with the charges. Okay, so you took in the charge away and you have a property called dipole moment. And here we don't have a luxury of the charges, so we're going to have the property called dipole moment by itself, and this is going to do mu. Mu is the symbol used for magnetic dipole moment, so this will be just magnetic dipole moment. Mu is not some qm times d, magnetic charge times d. It's not that. It's just itself is the basic property. Over here we had the luxury of thinking as a physical dipole and taking the limit. Here we don't have the luxury of thinking physical magnetic charge because we haven't really found a separate magnetic charge. Maybe someday somebody will find it and then the whole thing will have to be revisited. But right now, this is the fundamental thing we can think when thinking magnets. And that's why this problem is kind of from where you build. So suppose you do this problem, but so how can you use it to study real magnets? So suppose I have a real magnet, I have a real magnet, physical magnet. Well, what I can model with lots of point dipoles. And suppose I put them in some kind of external magnetic field. How would this magnet respond? Well, I can work out, say, force on each one of them and then sum them up. That will be the force on the whole magnet. That summing up will become an integral. So in principle, it can all be done. It's kind of very complicated. We're not going to go there for this problem. I just wanted to make sure that you understand what magnetic dipole moment is. Next thing you should know before you can answer this question is, suppose I got the magnetic dipole, I got mu, and I got the B, which is B is the B external, this external B. And so what's the formula for torque will be? Torque will be mu cross B. You can actually take this as a definition of torque, or you can actually derive this, but we'll just take the definition. The energy will be minus mu dot B. Is very much similar to what happens to electric dipole, right? And force will simply be minus del of U. As you know, if you know the potential energy, you can take a derivative and you can get the force. So this will be the formulas that you will need. And over here it looks like del mu dot B. Now mu is not dependent on x, y, z. So when you take a del, mu can come out, and it's going to be mu dot del B, and there will be other things. There's going to be like B dot del mu, then you're going to be mu cross del del cross B, and then you're going to have a B cross del cross mu. Yep. So this thing actually separates into 4 terms, and you are let me see, and you can say that this should be 0 because mu is gonna have a 0 derivatives, and this will be 0 because it's all derivatives of mu, components of mu. But this one is actually mu naught J, which is current density, and because at this point this whole thing is at point at this point, at that point, there is no current density. Current density is only on that z-axis for this particular magnetic field. So this is actually 0. So this is the only one that's left. So for the force, we can use del mu dot b, or I can use mu dot del b, whichever is more convenient. We'll use that. Okay, so with that, you should be able to set it up and do this problem. Okay, so maybe you want to go ahead and do it and come back and check my answer. Okay, let me do A, and should be a blueprint for doing the other ones, right? So what's the torque is going to be just mu cross B. So if I can write them out, that would be great, right? So what's the mu vector like? Mu vector is some mu, and it's along 15 degrees to the origin direction. So mu is going to be let's 15 degrees, let's call that phi, angle phi, and let's call this angle theta. Okay, so mu cosine phi I hat plus sine phi j hat. Of course, mu is this value. Okay, what's the b? B is going to be b, which is this value. Okay, because the unit vector is 1. So b equals to magnitude of this vector is 2 times 10 to the minus 4 over square x square plus y square. And at that point is going to be 2 times 10 to the power minus 4 and 1 centimeter, 1 centimeter. So this distance is square root 2 centimeters. So it's going to be square root 2 times 10 to the power minus 2 is square root 2 times 10 to the minus 2 Tesla. So that's yep. Okay, so that's the B, but the B direction is in the third direction. Cosine B is going to be in that direction. That means cosine theta I hat minus sine theta j hat. This is minus because it's in that direction, which you can place in that direction 90 degrees to this. So if I had xy direction, I have that point, so that's 45 this the theta. The B is in that direction, 90 degrees to that, and if you work it out, it's going to be cosine theta. So that direction is going to be minus cosine theta. It's going to be this whole thing cosine 90 degrees plus theta is going to be cosine 90 degrees cosine theta minus sine 90 degrees sine theta. So this is minus sine theta I hat plus cosine theta j hat, right? Yeah, so I had made a mistake over here. I just realized this should be minus sine theta I hat plus cosine theta j hat. I just see it now, and sine 90 degrees plus theta will simply be sine 90 degrees cosine theta plus 0. So it's going to be cosine theta plus cosine theta. Okay. So now we have mu and B. When you do a cross product, mu cross b, this with this will give me 0, so this will be I hat cross j hat will be k hat direction. It's going to be cosine phi cosine theta, and this will be the same way. J hat cross I hat give me negative, so it's going to come plus sine phi sine theta, and the other products will be 0. And so this whole thing is k hat mu b cosine theta minus phi, and so 45 degree minus, so this is 30 degrees. So this is going to be just very simply 2 times 10 to the power minus 5 and square root of 2 times 10 to the minus 2. Everything working on SI units. So this is Tesla, and this is Joule per Tesla, and then you have a cosine 30 degrees, which is square root of 3 over 2. So what I got is a square root of 6. This 2 will cancel this 2 times 10 to the power minus 7 joules, or Newton times meter. Joule is the same as Newton times meter. We use this when you say torque. We use this when we use energy. So the same units, but we use different for different purposes. Okay, so that's and this in the direction of k hat. So this torque is actually trying to lift it, rotate it in the direction of perpendicular to the B field and mu. Torque is mu cross B. So torque will be perpendicular to both of these. So torque direction is that way. So torque direction is so if this is mu direction and this is the B direction, and this is the XY plane, and so the torque direction is the axis of rotation. So torque direction is that direction in the z-axis direction. So this is the way it's trying to rotate. So it's trying to rotate it towards the B direction. It's trying to rotate towards the B direction. So in the end, mu will be kind of aligned with, mu will want to go over aligned with the B direction. Okay, so that's A. And a lot of the times people just ask A because the torque is the kind of one of the main properties, because you're going to align, and the energy will be associated with how much there's a misalignment and things like that. Okay, so to do B is let's do C first. So U equals to minus mu dot B. It's very simple. I got mu and B, and just take a dot product. That's just going to be mu times B minus mu times B, and this times this is going to be minus cosine phi sine theta, and then this times this is going to be plus sine phi cosine theta, and so minus mu B sine of theta minus phi. This I can pull this minus, and this will be plus minus sine of theta minus phi. So this is mu times B sine 30 degrees. And so we already know mu and B, and sine 30 degrees is going to be half mu and B. Mu is like a 2 times 10 to the minus 5, and B is a square 2 10 to the minus 2, and this is half, and so this is just a square root of 2 times 10 to the minus 7, and this is going to be joules. It's very simple, right? Once you figure out mu's and b's, in this notation is work out very nicely for us, right? Now, a lot of students make a mistake here and they go to C and they remember that F should be equal to minus del of U, and then they use U and then they say get a 0. This is totally wrong. This is U at one point, but the U is not the same at all the points, and so the derivative U will be obtained from the neighborhood, right? And so you got to do F equals to either del of mu dot B formula, or you're going to have mu dot del of the B formula. This is the B. You have to use this with all the dependencies that are there, okay? And once you're done, you can kind of plug things in. All right, so I'm going to do that out. Okay, so mu, let's do mu dot del del B. So B we already know. Mu, so mu has a mu x I hat plus mu y j hat. So mu x was mu cosine phi and mu y was mu sine phi from earlier. We already done this thing, right? Because like if this is x and y, then the mu is pointed in that direction phi, which is 15 degrees. So from there we just know mu x and mu y. So we just carry mu x and mu y. So this just turns out to be mu x, take derivatives of x, plus mu y, derivatives of y, of this B vector, which is B vector. And we know all the x's and things like that here, right? So we also gonna write x square plus y square. We're gonna write that as r, just for simplicity of the formula. And you can see dx of r is gonna be x over r, and dy of r is gonna be y over r. So it's gonna be a little hairy, but we can just try to do one and see how far we go. Dx with b will be and we can write 2 times 10 to the minus 4 is little b, just to keep notation simple, b, and then we have a dx which is x over r square I hat minus y over r square j hat, and then mu y b dy x over r square I hat minus y over r square j hat. And then we can kind of carry that out, mu x b, and go inside. Numerator just gives 1 over r square, and then we have a minus 2x over r cube, and then x over r, and this is I hat. And then we could do this out. Numerator gives me 0 first, and the denominator gives me y times 2x minus becomes plus over r cube j hat. So this is from the first one. And from the second one, I'm going to get a mu y b, and this is going to be almost like that, minus 2xy over r cube I hat minus, it's going to be almost like that. It's going to be 1 over r square minus 2y over r cube y over r, and then it's going to be j hat. Okay, so that looks very complicated expression, but that's what you're going to get. You're going to get a complicated expression, and we just have to work it out. So you can see mu x b over all of this. You can see I can do r square, or r to the power 4, mu br to the power 4. Mu x is mu cosine phi. So this is cosine phi multiplying these guys. You know, cosine phi is going to multiply these guys. You have r square minus 2x square I hat plus 2xy should have been r here times r here, because 2xy, this was going to be a j hat, and then times cosine phi, and this will be sine phi minus 2. Same thing happened over here, no? Let's see what happened here. So r cube, and then I did derivative and should get another r. So 2xy sine phi I hat minus this r square minus 2y square sine phi j hat. So now either you just go plug into this, or you can simplify further. Then use x equals to 1 centimeter, which is 10 minus 2 meter, and y equals to 1 centimeter is 10 minus 2 meter, and phi equals to 15 degrees. So using this, you should be able to get the answer. So I'm not going to complete it, but I just want to show you that sometimes the work is very and just tedious algebraically, but just in principle, these are the mechanical quantities we can actually get quite readily. But you have to be careful, you know, don't just take a derivative of a constant willingly, you know. These are important derivatives, and you need to be good in your Calc 3 to be able to do this kind of stuff. All right, let me just close this with some summary of the main formulas we have learned.